The Copernican principle asserts that no position in the universe is privileged, extending to the claim that, on large scales, the cosmos is statistically uniform and isotropic. This assumption is not philosophical but structural, embedded in the mathematical framework of modern cosmology. Yet observations challenge it. In 2005, data from the Wilkinson Microwave Anisotropy Probe revealed that the largest temperature fluctuations in the cosmic microwave background, the relic radiation from 380,000 years after the Big Bang, are not randomly distributed. Instead, they exhibit a coherent alignment across the sky. Subsequent measurements by the Planck satellite confirmed this anomaly with greater precision. Independent studies of quasar spin axes and galaxy cluster motions suggest a similar directional preference. The probability of such concordance arising by chance is exceedingly small. This unexpected alignment, termed the axis of evil, introduces a subtle but persistent tension within cosmology, hinting that the universe may possess an underlying structure or orientation not yet understood. The Copernican principle. The Copernican principle did not begin as a scientific claim, it began as a correction. When Nicholas Copernicus proposed in 1543 that the Earth orbits the Sun rather than the reverse, he was not merely solving an astronomical problem. He was initiating a philosophical revolution whose full consequences took centuries to unfold. Each subsequent generation of scientists extended the principle further, moving humanity's conceptual position from the center of the solar system to the outskirts of the galaxy, to an unremarkable region of an average galaxy in an ordinary cluster in a vast and undifferentiated universe. By the 20th century, the principle had become so embedded in scientific thinking that it was no longer even treated as an assumption requiring justification. It was treated as a background condition of rational inquiry, the baseline of intellectual humility that made objective science possible. In modern cosmology, the Copernican principle is formalized as the cosmological principle, which states that the universe is both isotropic and homogeneous. Isotropy means the universe looks the same in every direction from any given point. Homogeneity means it has the same properties at every location. Together, these two conditions justify the use of the Friedmann-Lemaitre-Robertson-Walker metric, the mathematical framework that describes how the geometry of the universe evolves over time under the influence of gravity and the energy content of space. The FLRW metric is the mathematical skeleton of Lambda CDM, the standard model of cosmology. It is the framework within which the Big Bang, the expansion of the universe, dark matter, dark energy, and the formation of large-scale structure are all described. Every quantitative prediction about the history and future of the universe that cosmologists make is derived from equations that depend, at their foundation, on the universe being isotropic and homogeneous. The observational evidence for this foundation is, on large scales, genuinely impressive. The cosmic microwave background is uniform in temperature to better than 1 part in 100,000 across the entire sky, confirming that the early universe was extraordinarily smooth. Galaxy surveys, extending to billions of light-years, show that on scales above roughly 300 million light-years, the distribution of matter is statistically uniform. No region is systematically denser or sparser than the average. The large-scale structure of the universe, the cosmic web of filaments and voids, is consistent with the statistical properties predicted by inflation-seeded perturbations in an isotropic background. These are not trivial agreements. They represent the convergence of decades of observation with the predictions of a mathematical framework that requires isotropy as an input. The cosmological principle is therefore not merely an assumption. It is a tested hypothesis that has survived decades of observational scrutiny at the scales where those observations are available. The crucial qualification is that phrase, at the scales where observations are available. The largest scales of the universe, the scales of the multipole moments of the cosmic microwave background, the scales at which coherent flows of galaxy clusters have been measured, the scales at which quasar spin alignments have been detected, are precisely where the cosmological principle is hardest to test and where the anomalies are appearing. The evidence that the principle holds on scales of hundreds of millions of light-years does not guarantee that it holds on scales of billions or tens of billions of light-years. And it is on those largest accessible scales that the data are beginning to show something unexpected. The philosophical stakes of a violation of the Copernican principle are distinct from the scientific ones and deserve separate consideration. If the largest structures in the observable universe are aligned with the plane of Earth's orbit around the Sun, there are essentially three possible explanations. The first is that the alignment is a coincidence, that it arose by chance from initial conditions that had no preference for any direction, and that we happen to be living in the particular realization of the universe that produced this coincidence. The second is that the alignment is a measurement artifact, that some systematic error in how we observe or analyze the cosmic microwave background is creating the appearance of an alignment that does not exist in the underlying reality. The third is that the alignment is physically real, that the universe genuinely has a preferred direction, and that this preferred direction is in some way related to the geometry of our solar system. The third possibility, if true, would be the most significant reversal of scientific thinking since Copernicus himself. It would imply either that the universe was shaped in a way that singles out our location, or that our location is not as unremarkable as 4 centuries of scientific progress have insisted. Multipole expansion and what it reveals. The cosmic microwave background is not a simple uniform glow. It contains temperature variations, tiny fluctuations at the level of 1 part in 100,000 relative to the average temperature of 2.725 Kelvin. That encode information about the physical conditions of the universe at the moment of recombination 380,000 years after the Big Bang. These temperature variations are distributed across the sky in a complex pattern, and extracting physically meaningful information from that pattern requires decomposing it into its constituent components, each of which corresponds to fluctuations on a specific angular scale. The mathematical tool for this decomposition is called multipole expansion. The principle of multipole expansion is analogous to Fourier analysis, the decomposition of a complex signal into a sum of simple oscillatory components of different frequencies. In the case of the cosmic microwave background, the decomposition is performed on the sphere of the sky, rather than along a one-dimensional time axis, and the basis functions are spherical harmonics, mathematical functions that describe oscillatory patterns across a spherical surface. Each spherical harmonic is characterized by 2 integers, the multipole moment number L, which determines the angular scale of the fluctuation, and the azimuthal index M, which determines the orientation of the pattern. The amplitude of the cosmic microwave background temperature variation at each combination of L and M is the coefficient of the corresponding spherical harmonic in the decomposition. The lowest order multipoles correspond to fluctuations on the largest angular scales, structures that span significant fractions of the sky. The dipole at L equals 1 describes a single hot-cold gradient across the full sky. It is dominated by the Doppler effect caused by the motion of the solar system through space at approximately 370 kilometers per second, relative to the rest frame of the cosmic microwave background, which shifts photons from ahead slightly bluer and from behind slightly redder. Because this motion is local and well understood, the dipole is subtracted from the maps before any cosmological analysis is performed. The quadrupole at L equals 2 represents the largest genuinely cosmological fluctuation accessible to observation. It divides the sky into 4 broad regions of alternating temperature excess and deficit. In the standard model of inflation, the quadrupole amplitude and orientation should be a random realization of a Gaussian probability distribution with no preferred orientation. The octopole, at L equals 3, represents the next scale down, dividing the sky into 8 regions. Again, in the standard inflationary model, its amplitude and orientation should be statistically independent of the quadrupole. There is no physical mechanism within the standard framework that should cause them to be correlated. The way the orientation of a multipole is defined quantitatively requires some care. For each multipole moment at order L, the pattern of temperature variations can be described by a set of 2 L+1 coefficients corresponding to the different values of the azimuthal index m from negative L to positive L. The power in the multipole and the orientation of its pattern on the sky are both encoded in these coefficients. For the quadrupole and octopole specifically, it is possible to define a characteristic axis, sometimes called the multipole vector or the axis of maximum angular momentum dispersion, that captures the dominant orientation of the fluctuation pattern. In a statistically isotropic universe, the quadrupole axis and the octopole axis should be oriented randomly and independently of each other. The probability that two randomly oriented unit vectors in three-dimensional space are separated by less than a given angle decreases rapidly as that angle decreases. And for truly random orientations, the expected angular separation is 90 degrees on average. The analysis that produced the axis of evil finding used exactly this framework. Researchers computed the quadrupole and octopole axes from the WMAP cosmic microwave background temperature maps and measured the angle between them. What they found was that the two axes were separated by only a few degrees, almost perfectly aligned. The probability of this alignment occurring by chance, if the two multipoles were truly statistically independent, as the standard model predicts, was calculated to be less than 1 in several hundred. But the surprise did not end with the mutual alignment of the quadrupole and octopole. When the combined axis, the direction around which both multipoles are jointly aligned, was projected onto a map of the sky in galactic coordinates, it was found to point toward the ecliptic plane of the solar system, and specifically toward the ecliptic poles. The angular separation between the axis of the quadrupole-octopole alignment and the ecliptic plane normal vector was only a few degrees. The probability of this additional coincidence occurring by chance was estimated at below 1% by most analyses, with some estimates reaching below 0.1%. The term axis of evil was applied to this finding not because it was necessarily physical, the possibility of a measurement artifact remained open, but because of the conceptual damage it inflicted. If the largest structures in the 13.8 billion year old universe were physically aligned with the orbital plane of a 4.5 billion year old solar system in an unremarkable corner of an unremarkable galaxy, the Copernican principle was either severely compromised or the data were wrong in a very specific and consequential way. Both possibilities were disturbing. The scientific community set out to determine which was true. The WMAP discovery. The Wilkinson Microwave Anisotropy Probe was launched by NASA in June 2001 and operated until 2010, producing 9 years of full-sky cosmic microwave background observations at 5 microwave frequency bands, ranging from 23 to 94 gigahertz. Its angular resolution reached approximately 0.2 degrees at the highest frequencies, sufficient to characterize the temperature fluctuation pattern across the full multipole range from the dipole through multipole moments in the thousands. WMAP's primary scientific contribution was the precise measurement of the acoustic oscillation peaks in the cosmic microwave background power spectrum, which provided tight constraints on the cosmological parameters of the Lambda CDM model. Its measurements confirmed the flat geometry of the universe, the relative proportions of ordinary matter, and dark energy, and the near-scale invariant spectrum of primordial fluctuations predicted by inflation. These headline results were robust, well understood, and broadly consistent with the standard model. The anomalies were quieter, emerging not from the headline science, but from detailed analyses of the angular distribution of power in the lowest multipole moments. The quadrupole anomaly had actually been noted even earlier in data from the COBE satellite launched in 1989, which found that the quadrupole power was significantly lower than the Lambda CDM model predicted, an observation sometimes called the quadrupole problem or the low quadrupole anomaly. WMAP confirmed the low quadrupole amplitude and added the more disturbing finding about its alignment with the octopole. The 2003 first-year WMAP data release included an analysis of the low multipoles that documented both the unexpectedly low quadrupole power and the alignment between the quadrupole and octopole axes. The initial paper by Tegmark, De Oliveira Costa, and Hamilton computed the multipole vectors for the quadrupole and octopole and found their mutual alignment to be statistically anomalous at a level that warranted serious attention. The term axis of evil was subsequently coined by Maguejo and Land in a 2005 paper that analyzed the full implications of the alignment and its relationship to the ecliptic plane. Their analysis showed that the quadrupole, the octopole, and several higher-order multipoles all showed a tendency to align with the ecliptic and with the direction of the CMB dipole, the direction of the solar system's motion through the cosmic microwave background rest frame. The WMAP team's own analysis acknowledged the anomalies but adopted a cautious position, noting that the low quadrupole amplitude and the alignments could in principle be explained by the specific realization of initial conditions that our universe happened to have, without requiring any new physics. In a universe as large as ours, rare statistical events occur with some frequency somewhere. The question was whether the combination of anomalies seen in the WMAP data was rare enough and consistent enough with a physical explanation to justify departing from the standard model. The WMAP team estimated the probability of the quadrupole-octopole alignment at roughly 1 in 60, which, while anomalous, was not catastrophically so. More detailed subsequent analyses that included the ecliptic alignment raised the statistical significance considerably. The detailed structure of the alignment was itself informative. The quadrupole and octopole patterns on the sky were not merely aligned in their dominant axes, they showed a more subtle correlation in their full two-dimensional structure, with the minima and maxima of the two multipoles organized in a way that was inconsistent with statistical independence. Some analyses found that the power in both the quadrupole and octopole was anomalously concentrated in a plane perpendicular to the ecliptic, a planar concentration that would be expected if the large-scale structure of the universe had some preferred orientation relative to the solar system's orbital plane. The physical interpretation of this concentration was unclear, but its statistical properties were confirmed by multiple independent groups using different analysis methods and different treatments of the galactic foreground. By the time the final 9-year WMAP data release appeared in 2012, the alignment anomalies had been confirmed in the higher sensitivity, better characterized maps. They had survived the progressive improvement in the foreground cleaning procedures that WMAP applied as more frequency bands and better modeling techniques became available. The question the scientific community was left with was whether they would survive the transition to the next generation of cosmic microwave background measurement, the Planck satellite, which offered substantially better sensitivity, angular resolution, and frequency coverage for separating cosmological signal from galactic foreground emission. The foreground problem. Before evaluating what the Planck satellite found, it is necessary to understand the foreground contamination problem in detail, because the foreground argument is the strongest and most technically substantive challenge to the reality of the axis of evil, and because understanding why it fails to fully explain the anomaly requires understanding exactly what the foreground consists of and how it is treated. The cosmic microwave background signal that reaches Earth's telescopes does not arrive through empty space. It arrives through the Milky Way galaxy, which extends across the sky as a broad band of emission, visible as the diffuse glow of the Milky Way to the naked eye, but extending across a far broader range of wavelengths, and with different emission mechanisms at different frequencies. At microwave frequencies, The three dominant foreground emission mechanisms are synchrotron radiation from relativistic electrons spiraling in the galactic magnetic field, free emission from ionized gas in the interstellar medium, and thermal emission from interstellar dust grains heated by starlight. Each of these mechanisms has a characteristic spectrum, the way the emission intensity varies with frequency, that differs from the blackbody spectrum of the cosmic microwave background. By observing the sky at multiple microwave frequencies and using the spectral differences to separate the foreground components from the cosmological signal, it is possible to construct cleaned maps of the cosmic microwave background temperature that have had the galactic contribution subtracted. The problem is that this separation is imperfect. The spectral shapes of the foreground components are not perfectly known. They vary across the sky as the physical conditions of the interstellar medium change, and the process of fitting and subtracting them introduces residuals that can mimic cosmological temperature fluctuations on large angular scales. The residuals are expected to be largest at the lowest multipole moments because the galactic foreground has the most power on large angular scales, and because the separation algorithms rely on having multiple frequencies to disentangle the signals, which is more effective on small angular scales, where the signal-to-noise ratio in individual pixels is higher. The galactic plane itself cannot be cleaned reliably. The foreground emission is too bright and too complex in the central region of the Milky Way for a reliable separation to be achieved with current methods. This necessitates the application of a galactic mask, a region of the sky around the galactic plane that is excluded from the analysis and replaced by an extrapolation or simply left as missing data. The mask introduces a complication for the multipole analysis because the spherical harmonic decomposition is defined for a complete spherical map, and cutting out a portion of the sphere changes the statistical properties of the decomposition in ways that must be carefully accounted for. Critics of the axis of evil finding pointed to both of these issues as potential sources of the anomaly. The argument regarding residual foreground contamination holds that the specific geometry of the Milky Way, which lies roughly in the plane of the solar system, since our solar system is embedded in the galactic disk, means that any residual galactic signal left in the cleaned maps would naturally appear to be correlated with the ecliptic plane. If the quadrupole and octupole axes are being partially determined by residual galactic emission rather than purely by the primordial signal, and if that residual emission is distributed roughly along the galactic plane, the alignment with the ecliptic would be an artifact rather than a physical reality. The argument regarding the mask holds that the specific shape of the galactic mask used in the WMAP analysis might be distorting the inferred multipole coefficients in a way that creates an apparent alignment. Different mask shapes give slightly different values for the reconstructed multipole coefficients, and if the analysis was performed with a mask whose geometry happened to introduce a bias toward the ecliptic alignment, the result might be an artifact of the analysis procedure rather than a property of the underlying cosmological signal. Both of these arguments are technically legitimate concerns that must be taken seriously. The WMAP analysis teams performed extensive tests to evaluate the robustness of the alignment findings against variations in the cleaning procedure, the mask shape, and the analysis method. The alignment persisted across these variations at a statistically significant level, but the tests were not exhaustive. The systematic error budget for low multipole analysis of a single frequency experiment like WMAP is genuinely large, and the possibility of an undiscovered systematic effect that consistently produced the ecliptic alignment could not be definitively ruled out. The foreground argument also faces a specific quantitative challenge. For residual galactic emission to produce the observed alignment with the ecliptic, it would need to have a very specific geometry, concentrated precisely in the ecliptic plane rather than uniformly in the galactic plane. The galactic plane and the ecliptic plane are not the same thing. They are tilted relative to each other by approximately 60 degrees. A residual galactic signal would naturally be aligned with the galactic plane, not the ecliptic plane. Producing an alignment with the ecliptic from galactic residuals therefore requires a specific pattern of residuals that is concentrated preferentially along the projection of the ecliptic onto the sky, which is not the natural geometry of the dominant foreground sources. This does not make the foreground explanation impossible, but it makes it quantitatively more difficult to sustain. What Planck found. The Planck satellite was the European Space Agency's third-generation cosmic microwave background mission, launched in May 2009 and operating until October 2013. Its scientific instrument suite consisted of two focal plane arrays: the low-frequency instrument, operating at 30, 44, and 70 GHz, and the high-frequency instrument, operating at 100, 143, 217, 353, 545, and 857 GHz. The combination of 9 frequency bands spanning more than an order of magnitude in frequency gave Planck an unprecedented capability for separating galactic foreground emission from the cosmological signal, because the spectral shapes of the different foreground components could be characterized far more completely than with WMAP's 5 bands. The angular resolution of Planck reached approximately 5 arc-minutes at the highest frequencies, and its sensitivity per resolution element exceeded WMAP's by a factor of roughly 3. These improvements were specifically relevant to the axis of evil debate. If the alignment anomaly was driven by residual galactic foreground contamination, Planck's better frequency coverage should produce cleaner maps with smaller residuals, and the alignment should weaken or disappear. If the alignment was driven by a particular mask geometry, Planck's different scanning strategy and different noise properties would motivate different mask choices, and a change in the mask should change the inferred alignment. If the alignment was a real cosmological feature, it should persist in Planck's maps essentially unchanged. The first Planck data release in March 2013 contained the Planck collaboration's own analysis of the large-scale cosmic microwave background anomalies. The results were unambiguous in one respect and carefully qualified in another. The unambiguous result was that the large-scale anomalies persisted. The quadrupole-octopole alignment was confirmed at a statistical significance, comparable to or slightly exceeding the WMAP finding. The low quadrupole power anomaly was confirmed. The alignment with the ecliptic plane was confirmed. These features were present in Planck's maps cleaned using multiple independent component separation methods, algorithms with very different mathematical approaches to the foreground separation problem, all giving consistent results for the large-scale temperature patterns. The persistence across independent component separation methods strongly argued against the alignment being a consequence of a specific artifact in the foreground cleaning procedure. The careful qualification was that the Planck team did not describe the anomalies as evidence for new physics. They described them as statistically significant departures from the predictions of the standard Lambda CDM model of inflation, whose origin remained uncertain. The team explicitly noted that the anomalies might represent rare fluctuations in an otherwise standard cosmology, or might reflect systematics not yet identified, or might require an extension of the standard model. They declined to interpret the ecliptic alignment specifically as a sign that the cosmological principle was violated, noting that the alignment with the ecliptic could still, in principle, reflect some unidentified systematic related to the geometry of the observation rather than a physical property of the universe. The subsequent Planck data releases in 2015 and 2018, incorporating the full mission dataset and refined analysis procedures, continued to confirm the anomalies without providing a definitive physical explanation. The 2018 Planck Cosmological Parameters paper, which represented the definitive cosmological analysis of the Planck mission, noted that the large-scale anomalies remained present in the final data products and remained without satisfactory explanation within the standard model. The paper also presented an analysis of the Planck polarization data for the large-scale anomalies, which showed results partially consistent with the temperature anomalies, but with lower statistical significance due to the lower signal-to-noise ratio of the polarization maps at the relevant angular scales. The polarization measurement is critical because it provides a qualitatively independent probe of the same physical conditions. The temperature and polarization fluctuations of the cosmic microwave background are generated by the same physical processes, the acoustic oscillations of the photon baryon plasma before recombination, and their statistical properties are tightly correlated in the standard model. If the quadrupole-octopole alignment in temperature is a real cosmological feature rather than an artifact, it should produce a corresponding alignment in the polarization maps. If it is an artifact specific to the temperature measurement, perhaps related to a systematic effect that does not affect polarization the same way, the polarization maps should show a different or absent alignment. The Planck polarization analysis found tantalizing but inconclusive hints of an alignment in the polarization data, consistent with both possibilities within the measurement uncertainties. The definitive test of the alignment through polarization awaits the next generation of cosmic microwave background polarization experiments. The statistical argument. The assessment of whether the axis of evil constitutes a genuine anomaly or a statistical fluctuation depends critically on how the statistical test is constructed, and the debate over the correct statistical framework has been at least as contentious as the debate over the physical origin of the alignment. Understanding the statistical argument requires grappling with several conceptual issues that do not arise in simpler scientific hypothesis tests. The fundamental challenge is the look elsewhere effect, also called the multiple comparisons problem. In particle physics, the discovery threshold of 5 sigma, a result that would occur by chance in fewer than 1 in 3.5 million random experiments, was established specifically to guard against the tendency to identify statistical fluctuations as discoveries when searching through large datasets with many possible discovery channels. The same logic applies to searches for anomalies in the cosmic microwave background. The CMB map contains information across a wide range of angular scales, and any given dataset will contain some unusual features somewhere. The question is whether the specific anomaly that was found was the subject of a pre-specified hypothesis, or was identified post hoc after examining the data. The axis of evil falls into a middle ground that makes its statistical interpretation genuinely contested. The alignment between the quadrupole and octopole is not obviously the result of a data dredging exercise in which thousands of possible anomalies were examined and the most significant one was reported. The specific prediction that the quadrupole and octopole should be statistically independent is a genuine, unambiguous prediction of inflation-based cosmology, and finding that they are correlated is a legitimate test of that prediction. In this sense, the axis of evil finding is not vulnerable to the look elsewhere criticism, in the same way that an anomaly identified by searching through all possible correlations in a dataset would be. However, the additional finding that the alignment is with the ecliptic plane rather than some other direction does introduce a look elsewhere concern, because the ecliptic alignment was identified after the quadrupole-octopole correlation was established, and there are several other directions: the galactic plane, the supergalactic plane, the CMB dipole direction, that would have been regarded as equally remarkable if the alignment had been with one of those instead. Analysts who have attempted to account for this post hoc selection by computing the probability of finding an alignment with any one of the several relevant reference frames, rather than with the ecliptic, specifically find somewhat reduced statistical significance, though the result remains anomalous at levels between 2 and 4 sigma, depending on the specific analysis. The more fundamental statistical issue concerns the validity of the probability estimates themselves. The probability calculations that give figures like less than 1 in 1,000 for the ecliptic alignment are derived from Monte Carlo simulations, large numbers of synthetic cosmic microwave background maps, generated from the standard model of inflation, in which the fraction of simulations showing alignment as extreme as the observed case is counted. These simulations are based on the assumption that the standard model is correct and that the only deviations from the model are random Gaussian fluctuations. If the standard model has systematic mismatches with reality at the largest scales, for example, if the primordial power spectrum is not exactly scale invariant at the lowest multipole moments, then the simulations are not the correct reference distribution, and the probability estimates derived from them may be wrong. This concern is sharpened by the low quadrupole power anomaly. The observed power in the CMB quadrupole is below the central prediction of the standard model at a level that is statistically anomalous, roughly at the level of 2 to 3 sigma, depending on the analysis. If the quadrupole power is genuinely suppressed relative to the standard model prediction, the standard model simulations overestimate the typical quadrupole amplitude, which could affect the alignment statistics. Some researchers have argued that a model with suppressed large-scale power, perhaps from a specific feature in the primordial power spectrum or from a specific topology of the universe, would produce a different distribution of alignment statistics, potentially making the observed alignment less anomalous within the modified framework. Despite these complications, the statistical case for the axis of evil as a genuine anomaly has strengthened over time rather than weakened, primarily because the same directional bias has appeared in independent datasets whose statistical properties are unrelated to the cosmic microwave background analysis. When the probability estimates for the CMB alignment are combined with independent probability estimates for the dark flow of galaxy clusters and the spin alignment of quasars, the combined statistical significance grows substantially. Whether all of these signals are aspects of the same underlying physical phenomenon is itself an open question, but their mutual consistency makes the case for systematic measurement error progressively harder to sustain. The Planck polarization tests. The cosmic microwave background carries information in two distinct physical channels: the temperature fluctuations, which reflect the density and velocity variations of the photon baryon plasma at the moment of recombination, and the polarization of the radiation, which reflects the local quadrupole anisotropy of the radiation field at the same moment. Both channels encode information about the same primordial perturbations, but through different physical mechanisms, and their statistical properties are related by the standard model in specific, testable ways. The polarization of the cosmic microwave background comes in two patterns: the curl-free E-mode polarization, which is the stronger signal and is produced by both scalar and tensor perturbations of the primordial plasma, and the divergence-free B-mode polarization, which is produced only by tensor perturbations, gravitational waves from inflation, and by the gravitational lensing of E-modes by intervening large-scale structure. For the axis of evil specifically, the E-mode polarization is the most relevant diagnostic. Because the temperature and E-mode polarization fluctuations are generated by the same acoustic oscillations, they are correlated in the standard model through a well-defined cross-power spectrum. On large angular scales, corresponding to the quadrupole and octopole, this temperature polarization correlation should reflect the same alignment structure as the temperature alone if the alignment is a real cosmological feature. If the alignment is an artifact of the temperature analysis, perhaps from a systematic effect specific to the temperature measurement chains, or from a specific pattern of foreground residuals, the E-mode maps derived from a different set of detector channels and analyzed with different cleaning algorithms should show a different pattern. The Planck mission's polarization analysis at large angular scales was complicated by systematic effects in the low-frequency instrument's polarization data that required extensive characterization and correction. The primary systematic concern was the coupling between the temperature and polarization measurements through effects related to the spacecraft's attitude reconstruction, the beam asymmetry of the individual detectors, and the bandpass mismatch between polarization-sensitive detectors that were designed to be matched but had small residual differences. These systematics were particularly important at large angular scales. exactly the scales relevant to the axis of evil, because they grew larger relative to the cosmological signal as the angular scale increased. The Planck collaboration's assessment of the polarization systematics at low multipoles concluded that the 2018 data release's large-scale polarization maps had residual systematic contamination at a level that prevented them from being used for definitive cosmological analysis of the lowest multipole moments. Despite this caveat, multiple independent research groups analyzed the available Planck polarization data for evidence of the quadrupole-octopole alignment and related large-scale anomalies. The results were consistent in their ambiguity. Some analyses found evidence for a preferred direction in the E-mode polarization maps that was statistically consistent with the temperature alignment, at a significance level that ranged from marginal to moderately strong, depending on the specific analysis choices. Other analyses, applying more conservative treatments of the systematic uncertainty, found results consistent with statistical isotropy within the larger error bars that the systematics introduced. The polarization data were neither a clear confirmation of the axis as a real physical feature, nor a clear refutation of it. They were simply insufficient to resolve the question, given the level of systematic contamination at the relevant scales. This situation is the primary scientific motivation for the next generation of ground-based cosmic microwave background polarization experiments. The Simons Observatory, currently being commissioned in the Atacama Desert in Chile, and the planned CMB-S4 experiment will measure the E-mode polarization of the cosmic microwave background at large angular scales with substantially lower systematic contamination than Planck achieved. The combination of lower instrumental systematics, different scanning strategies that produce different patterns of systematic coupling, and independent frequency coverage that enables independent foreground separation will provide the definitive test of whether the large-scale temperature anomalies are reflected in the polarization maps. If they are, if the quadrupole-octopole alignment appears in the E-mode maps with statistical significance comparable to the temperature anomaly, the case for the axis as a real physical feature of the universe will be extremely difficult to dispute. If they are not, if the polarization maps show a statistically isotropic distribution at large scales, while the temperature maps continue to show the alignment, the most likely interpretation will be that the temperature alignment is driven by some unidentified systematic effect that does not couple to the polarization channels in the same way. The dark flow. The axis of evil found in the cosmic microwave background would remain a provocative but isolated anomaly if it were the only dataset showing a preferred direction. Its scientific significance escalates dramatically when it is placed in the context of independent observational evidence from completely different physical systems that suggests the same directional bias. The most compelling of these independent signals is the phenomenon known as dark flow, the apparent coherent bulk motion of thousands of galaxy clusters toward a specific region of the sky, over and above any motion attributable to the gravitational influence of known mass concentrations within the observable universe. Dark flow was first reported in 2008 by Alexander Kashlinsky and colleagues at NASA's Goddard Space Flight Center, based on a measurement technique called the kinetic Sunyaev-Zeldovich effect. The kinetic Sunyaev-Zeldovich effect is the distortion of the cosmic microwave background spectrum that occurs when CMB photons scatter off the hot ionized gas within galaxy clusters that are moving with respect to the CMB rest frame. When a galaxy cluster moves toward us, it scatters photons to slightly higher energies, producing a small temperature increment in the CMB at the location of the cluster. When it moves away from us, it scatters photons to lower energies, producing a small temperature decrement. The magnitude of this effect is proportional to the line-of-sight velocity of the cluster relative to the CMB rest frame, its peculiar velocity, and to the optical depth of the cluster's gas-to-electron scattering. By measuring the kinetic Sunyaev-Zeldovich signal from a large sample of galaxy clusters at different locations across the sky, It is possible to look for coherent patterns in their peculiar velocities that would indicate a systematic bulk flow of the cluster population. In a universe that is homogeneous and isotropic on the largest scales, the peculiar velocities of galaxy clusters at large distances should be randomly oriented. Any large-scale coherent flow should have dissipated during the Hubble time, as the expansion of the universe diluted the momentum. Gravitational perturbations from known mass concentrations within the observable universe, including the Great Attractor, the Shapley supercluster, and other massive structures, can induce coherent flows on scales up to a few hundred megaparsecs. But these should be essentially absent at distances of 1 billion light-years or more. The Kashlinski analysis found a coherent bulk flow of galaxy clusters extending to distances of several billion light-years, moving at velocities of several hundred kilometers per second toward a direction in the southern sky, in the direction of the constellations Centaurus and Vela. This flow was not attributable to the gravitational influence of any known mass concentration within the observable universe. There is no structure visible in galaxy surveys at those directions and distances that could be generating the gravitational pull required to explain a multi-billion light-year coherent flow. The researchers proposed that the flow was generated by gravitational attraction toward a mass concentration outside the observable universe, a structure beyond the cosmic horizon whose gravitational influence was reaching across the boundary of the observable cosmos and pulling on the matter within it. The direction of the dark flow was subsequently found to be broadly consistent with the direction of the axis of evil as measured from the cosmic microwave background, the same general region of the southern sky that the quadrupole-octopole alignment points toward. This consistency between two completely independent datasets, the temperature pattern of the oldest light in the universe and the velocity pattern of modern galaxy clusters measured through a physically distinct mechanism, was striking, because the two measurements have entirely different systematic error budgets. The cosmic microwave background measurement is sensitive to the specific pattern of foreground contamination in the galactic plane and to the specific analysis methods used to clean and decompose the maps. The kinetic Sunyaev-Zeldovich measurement is sensitive to the systematic effects of cluster detection, the calibration of the cluster gas optical depth, and the modeling of the contaminating signals from other CMB emission components. A systematic error that produced a spurious alignment in the CMB temperature maps would not simultaneously produce a spurious coherent motion in the kinetic Sunyaev-Zeldovich dataset. Subsequent analyses of the dark flow using larger cluster samples and improved kinetic Sunyaev-Zeldovich measurements from the Planck satellite have produced mixed results. Some groups found reduced statistical significance for the dark flow signal when applying more conservative treatment of systematic uncertainties and when using the Planck cluster catalogue rather than WMAP selected clusters. Other groups, using different cluster selection criteria and analysis methods, continued to find evidence for a coherent, large-scale flow consistent with the original Kashlinski finding. The controversy over the dark flow closely mirrors the controversy over the CMB alignment. The signal is present in some analyses and marginal or absent in others, with the differences largely attributable to choices in the treatment of systematic effects and the statistical framework applied. As of 2025, the dark flow remains a contested observational claim whose resolution requires better kinetic Sunyaev-Zeldovich measurements from the next generation of CMB experiments, which will have the sensitivity to detect cluster peculiar velocities at cosmological distances with much higher signal-to-noise than currently available. Quasar spin alignments. The dark flow anomaly is compelling precisely because it uses galaxy clusters as test particles in a velocity field, probing the large-scale kinematic structure of the universe through a mechanism entirely independent of the cosmic microwave background. But it is not the only independent dataset that has produced evidence of a preferred direction on cosmological scales. A second, structurally distinct line of evidence comes from the spin axes of quasars, the luminous active galactic nuclei powered by accreting supermassive black holes, which have been found in multiple surveys to exhibit coherent alignments across distances of several billion light-years. The quasar spin alignment signal is, in some respects, even more difficult to explain than the dark flow, because the physical mechanism by which a black hole acquires its spin axis is set during the formation and early evolution of its host galaxy. And there is no standard process within Lambda CDM that should produce correlated spin orientations between objects separated by distances far larger than the scale of causal contact during structure formation. The spin axis of a quasar is not directly observable as a vector in three-dimensional space. It is inferred from the orientation of the quasar's emission features, specifically from the position angle of the radio jets that are ejected along the rotation axis of the accretion disk surrounding the central black hole, and from the polarization angle of the optical emission. Both proxies have uncertainties, and both require careful calibration and modeling to extract a reliable estimate of the underlying spin axis orientation. The position angle of a radio jet is the most direct proxy, since relativistic jets are launched perpendicular to the accretion disk plane and therefore parallel to the black hole's angular momentum vector. The optical polarization angle is less directly related to the spin axis, but provides a complementary measurement for quasars where radio jet morphology is not available. The first statistically significant evidence for large-scale quasar spin alignment was reported by Hutzemakers and colleagues using optical polarization measurements of quasars drawn from the European Southern Observatory's Very Large Telescope and earlier ground-based surveys. Their analyses, beginning in the early 2000s and refined through subsequent work in 2014 and 2022, found that the optical polarization angles of quasars in large coherent regions of the sky, regions spanning several hundred megaparsecs to over a gigaparsec, were aligned with each other at a level inconsistent with random orientations. The alignment was not uniform across the sky, but was organized into coherent domains, within each of which the quasar polarization angles were statistically consistent with a single preferred orientation. The boundaries between these domains did not correspond to any known large-scale structure in the galaxy distribution, and the scale of the domains, approximately 1 billion light-years across, exceeded the scale of any known physical process that could coordinate spin alignments. The 2014 analysis by Temple and Libeskind used a different approach, examining the alignment between the spin axes of galaxies and the filaments of the cosmic web in which those galaxies were embedded. They found that the spin axes of galaxies in low-mass groups tended to be aligned parallel to the filament axis, while the spin axes of galaxies in high-mass clusters tended to be perpendicular. This mass-dependent alignment with the cosmic web is predicted qualitatively by simulations of structure formation, in which the angular momentum of halos is acquired through tidal torquing from the surrounding large-scale density field. But the amplitude of the observed alignment in real data exceeded the predictions of standard simulations at the largest scales, suggesting that either the tidal torque mechanism was more efficient than models assumed, or that an additional source of large-scale coherence was operating beyond what Lambda CDM could generate. The most directly relevant result for the axis of evil question came from a series of analyses of radio quasars using the Very Large Array and the Giant Meter Wave Radio Telescope, particularly the work of Taylor and Jagannathan, published in 2016, using the Taylor-Jagannathan catalogue of radio galaxies. Their analysis found that the position angles of radio jets, the most direct proxy for black hole spin axis orientation, were aligned across scales of up to 1 billion light-years in a specific region of the sky. The alignment axis in this region was broadly consistent with the direction of the axis of evil from the cosmic microwave background. Subsequent work by Contigiani and colleagues in 2017 used a larger sample of radio galaxies from the first survey to test whether the Taylor-Jagannathan alignment was a general feature of the radio galaxy population or a localized effect. Their analysis found weaker but still statistically significant alignment at the largest scales probed by the survey, with a preferred orientation that again showed consistency with the CMB alignment direction. The 2022 and 2023 analyses, using data from the Meerkat radio telescope in South Africa and the low-frequency array in Europe, added substantially to the sample size and frequency coverage available for this kind of study. Meerkat's high sensitivity at frequencies between 900 MHz and 1.67 GHz enabled the detection of extended radio jet structures in sources that were too faint for reliable morphological classification in earlier surveys, and the resulting catalogues of jet position angles for tens of thousands of radio galaxies provided the most powerful statistical test yet available. The Meerkat-based analyses found alignment signals consistent with earlier results, but with larger statistical samples that reduced the uncertainties substantially. The preferred orientation of the alignment in the Meerkat data projected onto the celestial sphere was found to be within approximately 15 degrees of the axis of evil direction from the Planck cosmic microwave background maps, a consistency that, given the independent nature of the two measurements and their entirely different systematic error budgets, is difficult to attribute to a common instrumental artifact. A critical question for interpreting these results is whether the large-scale quasar spin alignments could be produced by known physical processes within the standard cosmological model, without invoking any violation of isotropy at the fundamental level. The tidal torque theory of angular momentum acquisition predicts that the spin axes of halos should be correlated with the tidal tensor of the large-scale density field in their vicinity, which itself reflects the large-scale structure of the cosmic web. On scales of tens of megaparsecs, this correlation is expected and has been confirmed in simulations. On scales of hundreds of megaparsecs to gigaparsecs, however, the tidal field should be incoherent. The cosmic web on those scales consists of many independent filaments and voids whose orientations are not correlated in the standard model. Producing spin alignments on gigaparsec scales through tidal torquing would require a coherent tidal field on those same scales, which in turn would require a density perturbation of corresponding amplitude. And no such perturbation is consistent with the observed large-scale structure of the universe as measured by galaxy surveys. The absence of a standard physical explanation for gigaparsec scale spin alignments is what elevates the quasar data from an interesting curiosity to a potential component of the same underlying phenomenon as the CMB alignment and the dark flow. All three datasets are pointing in the same general direction, using physically distinct tracers and entirely different measurement technologies. The CMB temperature maps encode the density and velocity field of the photon baryon plasma at redshift approximately 1000. The dark flow measurement encodes the peculiar velocity field of galaxy clusters at redshifts between 0 and 1, cosmic times ranging from the present to roughly 6 billion years ago. The quasar spin alignments encode the angular momentum field of accreting black holes at redshifts between 0 and 2, covering the period from approximately 3 billion years ago to the present. That a directional preference appears consistently across all three tracers, across redshifts spanning most of the observable history of the universe, is the core of the multi-messenger case for the axis of evil as a physical reality rather than a measurement artifact. The hemispheric power asymmetry. Alongside the quadrupole-octupole alignment, the Planck and WMAP data contain a second large-scale anomaly that has received less public attention, but is statistically comparable in its significance and physically related in its implications. This anomaly is called the hemispheric power asymmetry. The observation that the amplitude of temperature fluctuations in the cosmic microwave background is systematically higher in one hemisphere of the sky than in the opposite hemisphere, when the sky is divided along a specific great circle. The asymmetry is not a subtle effect buried in the noise. The ratio of power in the two hemispheres differs by approximately 7%, and the direction of the asymmetry axis, the axis perpendicular to the dividing great circle, is aligned with the axis of evil to within approximately 20 degrees. The hemispheric asymmetry was first identified in the first-year WMAP data by Ericsson and colleagues in 2004. Their analysis applied a local power spectrum estimator, a technique that measures the amplitude of temperature fluctuations within a patch of sky centered on each point, effectively mapping the spatial variation of CMB power across the full sky. What they found was that the local power was not uniform. It was systematically higher in a region centered roughly on the galactic coordinates corresponding to the southern ecliptic hemisphere, and lower in the opposite direction. The asymmetry was present across a range of angular scales from approximately 2 degrees to 10 degrees, corresponding to multipoles between roughly 20 and 90, and was not attributable to any single localized feature in the map. The dipolar modulation model, in which the CMB temperature field is multiplied by a slowly varying function that has a dipolar angular dependence across the sky, was developed to parameterize this asymmetry quantitatively. In this model, the temperature at each point on the sky is the product of the standard isotropic signal, and a factor of the form 1 plus a times the cosine of the angle from the preferred direction, where a is the asymmetry amplitude and the preferred direction is the axis of maximum power. Fitting this model to the WMAP and Planck data gives an asymmetry amplitude of approximately 3 to 7%, depending on the range of angular scales included in the fit, with the preferred direction consistently pointing toward the same region of the southern sky as the quadrupole-octopole alignment axis. The Planck collaboration confirmed the hemispheric power asymmetry in all of its major data releases, using multiple independent analysis methods and multiple foreground cleaned maps. The asymmetry is present in all 4 of the Planck component separation products: SMICA, NILC, CVEM, and Commander, each of which uses a different algorithm to separate the CMB signal from galactic and extragalactic foregrounds. Its persistence across independent analysis methods argues strongly against a foreground origin because the foreground residuals in the 4 methods have different spatial distributions and spectral properties and would be expected to produce different asymmetry patterns if the asymmetry were driven by foreground contamination. The statistical significance of the hemispheric asymmetry in the Planck data is between 2 and 3 sigma, comparable to the CMB dipole modulation signal and to the quadrupole-octopole alignment. Not individually decisive, but collectively important as part of the broader pattern of directional anomalies. The physical interpretation of the hemispheric asymmetry is constrained by the angular scale dependence of the signal. The asymmetry is most prominent at multipoles between approximately 20 and 600, a range of angular scales that corresponds to physical scales between roughly 40 and 1200 megaparsecs at the distance of the last scattering surface. At multipoles below 20, the scales of the quadrupole and octopole, the asymmetry is consistent with but not required by the data at high significance, due to the large cosmic variance at those scales. At multipoles above approximately 600, the asymmetry amplitude decreases, suggesting that whatever physical mechanism produces the asymmetry is associated with structures larger than the characteristic scale of the acoustic horizon at recombination, approximately 150 megaparsecs. This scale dependence constrains the class of physical models that can explain the asymmetry. It must be a feature of the very large-scale initial conditions rather than of local structure, and it must have an angular scale much larger than the standard inflationary correlation length. Several theoretical mechanisms have been proposed to explain the hemispheric asymmetry within an extended cosmological framework. A superhorizon adiabatic perturbation, a density fluctuation whose wavelength exceeds the current Hubble radius of approximately 14 billion light-years, would modulate the amplitude of the observed temperature fluctuations differently in different directions, producing a dipolar asymmetry whose magnitude and scale dependence are broadly consistent with the observations. The required perturbation amplitude is approximately 3% on superhorizon scales, which is not excluded by any current observational constraint since superhorizon modes are not directly observable and their amplitude is not constrained by the power spectrum at smaller scales. A variant of inflation in which the primordial power spectrum is not perfectly scale invariant but has a directional dependence, introduced either by an anisotropic inflationary expansion or by a preferred direction component in the inflaton potential, would produce a similar pattern. The connection between the hemispheric asymmetry and the quadrupole octopole alignment in the same preferred direction makes the superhorizon perturbation model particularly attractive, because a single superhorizon mode with amplitude of a few percent could simultaneously produce both the asymmetry and the alignment by breaking the statistical isotropy of the primordial fluctuations on the largest observable scales. The multi-messenger case. The concept of multi-messenger astronomy was formalized in the context of gravitational wave detection, the idea that a single astrophysical event observed simultaneously through gravitational waves, electromagnetic radiation, and neutrinos provides constraints that no single channel could achieve alone. The axis of evil presents an analogous situation at cosmological scales. No single dataset, neither the CMB temperature alignment, nor the dark flow, nor the quasar spin distribution, individually constitutes decisive evidence for a preferred direction in the universe. Each can be argued away, with varying degrees of plausibility, as a systematic artifact of its specific measurement technique. But the consistency of the directional signal across all three channels, given that they have entirely independent systematic error budgets, changes the epistemological status of the claim in a way that is qualitatively different from any single channel argument. The formal combination of independent probability estimates from multiple datasets is a standard procedure in physics, governed by the principle that statistically independent measurements can be combined multiplicatively in their probability values. If the CMB temperature alignment has a probability of arising by chance of approximately 1%, and the dark flow signal has an independent probability of approximately 2 to 3%, and the quasar spin alignment has an independent probability of approximately 1 to 2%. The combined probability of all three occurring simultaneously by chance, assuming independence, is of order 1 in a million or less. This calculation is approximate, and its precise numerical value depends strongly on the specific analyses used to derive each individual probability estimate, but the qualitative conclusion is robust. The combination of independent directional signals is far more statistically significant than any individual signal. The independence of the systematic errors is the crucial assumption in this argument, and it deserves careful scrutiny. Could there be a common systematic effect that simultaneously biases the CMB temperature maps toward the ecliptic, produces a spurious coherent flow in the kinetic Sunyaev-Zeldovich signal, and introduces a spurious alignment in the radio jet position angles of thousands of quasars? Such a common systematic would need to operate across fundamentally different physical measurements: microwave photons from the surface of last scattering, the inverse Compton scattering of those same photons off hot intracluster gas, and the synchrotron emission from relativistic jets launched by spinning black holes billions of light years away. The systematics relevant to each measurement are completely different. The CMB temperature analysis is sensitive to galactic dust emission, the WMAP and Planck beam properties, and the specific algorithms used to decompose the spherical harmonic coefficients. The kinetic Sunyaev-Zeldovich measurement is sensitive to the cluster selection function, the modeling of the thermal Sunyaev-Zeldovich signal that must be subtracted, and the calibration of the cluster optical depth. The radio jet alignment measurement is sensitive to the source classification algorithms, the signal-to-noise cuts applied to select reliable morphologies, and the correction for the observational bias introduced by projection onto the plane of the sky. No physically plausible common systematic simultaneously distorts all three measurements in the same direction. The directional consistency itself can be quantified more carefully. The axis of evil from the CMB temperature maps points toward ecliptic coordinates that correspond to a galactic longitude of approximately 240 degrees and a galactic latitude of approximately 60 degrees in the southern sky, near the boundary of the constellations Virgo and Hydra in the direction of the Vela Centaurus region. The dark flow direction reported by Kashlinsky and colleagues points toward galactic longitude approximately 283 degrees and galactic latitude approximately 12 degrees, broadly consistent with the same southern sky region but offset by several tens of degrees. The quasar spin alignment preferred direction from the Taylor-Jagannathan analysis points toward a position broadly consistent with both, within the angular uncertainties of each measurement. These three directions are not exactly coincident. They span a region of sky on the order of 40 to 60 degrees across, but given the measurement uncertainties in each dataset and the different physical traces involved, this level of directional consistency is remarkable. A truly random set of three preferred directions would, on average, be separated by 90 degrees, and the probability of three independent random directions all falling within a 60-degree cap of sky is approximately 1 in 30, even before accounting for the fact that each individual direction is itself anomalous. The multi-messenger case has strengthened progressively since 2008, when the dark flow was first reported and placed in the context of the earlier CMB alignment. The quasar alignment data have been accumulating over the same period, and the consistency of the directional signal with each new dataset has deepened rather than dissolved. This trajectory is the opposite of what would be expected if the signals were artifacts of specific instruments or analysis choices. Artifacts typically weaken or disappear as measurements improve and analysis methods are refined. Instead, the axis signal has persisted through the transition from COBE to WMAP to Planck in the CMB, through the expansion of quasar spin catalogues from hundreds to tens of thousands of objects, and through the improvement of kinetic Sunyaev-Zeldovich sensitivity from marginal detection to robust measurement at individual cluster scales. The persistence is not proof of a physical origin, but it shifts the burden of explanation progressively toward those who maintain that all three signals are artifacts. The cold spot and the supervoid. No discussion of large-scale CMB anomalies is complete without addressing the CMB cold spot, a region of anomalously low temperature in the southern sky, centered at approximately galactic longitude 209 degrees and galactic latitude -57 degrees, that has been identified in the WMAP and Planck maps as one of the most statistically extreme features in the full sky CMB temperature distribution. The cold spot is not strictly part of the axis of evil finding. Its statistical anomaly is of a different character from the quadrupole-octopole alignment, but its proximity to the axis of evil direction, its persistence across satellite generations, and the discovery of a potential physical explanation for it have made it a significant secondary element of the broader case for large-scale anomalies in the CMB. The cold spot was first identified by Vielva and colleagues in 2004 using a wavelet analysis of the WMAP first-year data. The analysis applied a spherical Mexican hat wavelet transform to the CMB temperature map at a range of angular scales, and found that the amplitude of the wavelet coefficient at one specific location in the southern sky exceeded the expected range of a Gaussian random field, at a level corresponding to approximately 3 to 4 sigma in the tail of the distribution. The feature is not a simple circular depression in temperature. It has a complex internal structure with a cold central region of approximately 5 degrees in angular diameter surrounded by a warm ring. But its overall temperature decrement, relative to the surrounding CMB, is approximately 70 microkelvin, which is substantially below the range expected from Gaussian fluctuations. Cruz and colleagues confirmed the cold spot in 2005 using independent analysis methods and found that its probability of occurring in a standard Gaussian CMB realization was approximately 1.85%, anomalous, but not individually decisive. The Planck team confirmed the cold spot in all of its data releases using 4 different component separation methods and a range of statistical tests. The Planck analysis found the cold spot to be present in all cleaned maps at a consistent location and amplitude, with no evidence that its properties were sensitive to the specific foreground cleaning procedure. The probability of the cold spot arising by chance in a standard inflationary cosmology was estimated at between 1 and 2%, depending on the specific statistical test applied. The physical explanation for the cold spot has been debated since its discovery. The most popular early explanations invoked exotic physics, a cosmic texture, which is a topological defect formed during a phase transition in the early universe, a bubble collision in an eternal inflation scenario, or a void-induced effect through the Sachs-Wolf mechanism. The Sachs-Wolf mechanism is particularly relevant. As CMB photons travel through a large underdense region, a cosmic void, they gain energy falling into the gravitational potential of the void and lose energy climbing out. In a universe dominated by dark energy, the potential well of the void is shallower when the photons exit than when they entered, because dark energy causes the potential to decay. This is the integrated Sachs-Wolf effect, and it produces a cold imprint in the CMB at the location of large voids. The discovery of a large underdense region in the direction of the cold spot, reported by Sapudi and colleagues in 2015 using data from the WISE infrared survey and the 2 mass photometric redshift catalog, provided the first plausible physical explanation for the anomaly. The supervoid identified by Sapudi and colleagues has a radius of approximately 300 megaparsecs, a central underdensity of approximately 20% relative to the mean galaxy density, and is centered at a redshift of approximately 0.22, a distance of approximately 1 billion light-years. The integrated Sachs-Wolf imprint of such a void on the CMB is predicted to produce a temperature decrement of approximately 20 microkelvin, smaller than the full cold spot amplitude of 70 microkelvin, suggesting that the supervoid explains part, but not all of the anomaly. Subsequent analyses have found evidence for additional underdense structure along the line of sight to the cold spot that could account for more of the temperature deficit. But the full quantitative reconciliation between the observed cold spot amplitude and the integrated Sachs-Wolf effect of the observed voids remains imperfect. The relevance of the cold spot to the axis of evil is twofold. First, its angular position on the sky, in the southern hemisphere, broadly toward the Centaurus Vela region, places it in the same general quadrant as the axis of evil direction and the dark flow attractor. Second, if the cold spot is partially or fully explained by a supervoid, it demonstrates that the real large-scale structure of the universe contains features, underdensities of 300 megaparsecs radius and 20% contrast, that are themselves at or beyond the edge of what the standard model of structure formation predicts. The existence of such extreme voids in the distribution of matter, combined with the directional anomalies in the CMB and the coherent flows of galaxy clusters, paints a picture of the universe on its largest accessible scales as more structured, more anisotropic, and more extreme than the smooth Gaussian random field of standard inflation would produce. The Hubble tension connection. The axis of evil does not exist in isolation within the landscape of modern cosmological anomalies. It is embedded in a broader crisis of the standard model that includes a second, independently derived discrepancy of comparable severity, the Hubble tension. Understanding the relationship between these two anomalies requires first understanding what the Hubble tension is and why it resists resolution within the standard framework, and then examining the specific ways in which an anisotropic universe would naturally produce a Hubble tension as a secondary consequence. The Hubble constant, denoted h0, is the proportionality constant between the recession velocity of a distant galaxy and its distance, the fundamental measure of the expansion rate of the universe. In a homogeneous and isotropic universe described by the FLRW metric, the Hubble constant is a global quantity that has the same value regardless of the direction in which it is measured. There are two primary methods for measuring the Hubble constant from observations. The first, which operates entirely within the late universe at redshifts below approximately 2, uses the cosmic distance ladder, a chain of distance indicators beginning with geometric parallax measurements of nearby stars, extending through the period luminosity relationship of Cepheid variable stars to distances of roughly 50 megaparsecs, and culminating in the use of type Ia supernovae as standardizable candles at cosmological distances. The second method extracts the Hubble constant from the cosmic microwave background by fitting the full Lambda CDM model to the acoustic oscillation peaks, using the precisely measured angular scale of the first peak combined with the known sound horizon at recombination to infer the distance to the last scattering surface and thence the expansion history. The tension between these two measurements is now at a level of approximately 5 sigma, meaning that if both measurements are correct and their uncertainties are accurately estimated, the probability of the discrepancy arising by chance is less than 1 in a million. The distance ladder measurements, most precisely those from the SH0ES collaboration using Hubble Space Telescope observations of Cepheid variables and supernovae, give a Hubble constant of approximately 73 km per second per megaparsec. The CMB-based measurement from Planck, which requires assuming a cosmological model to convert the observed angular power spectrum into a distance and expansion rate, gives approximately 67.4 km per second per megaparsec. The discrepancy of roughly 5.5 km per second per megaparsec, about 8% of the central value, is far larger than the stated uncertainties of either measurement, and it has resisted explanation through systematic errors in either method, despite intense scrutiny of both over the period from 2016 to the present. The connection between the Hubble tension and the axis of evil was first explored systematically in papers by Migkus and colleagues published in 2020 and 2021, using X-ray observations of galaxy clusters from the XMM Newton and Chandra satellites to measure the Hubble constant as a function of direction on the sky. Galaxy clusters emit X-rays through thermal Bremsstrahlung, the electromagnetic radiation produced when electrons decelerate in the Coulomb field of ions in the hot intra-cluster gas. The luminosity of this emission is tightly correlated with the temperature of the gas through scaling relations that are understood from both observations and hydrodynamic simulations. By measuring the X-ray temperature of a cluster and using the luminosity temperature scaling relation to infer the intrinsic luminosity, the distance to the cluster can be estimated from the observed flux, providing an independent distance measurement that is not part of the standard cosmic distance ladder. Migkus and colleagues applied this technique to a sample of several hundred galaxy clusters distributed across the sky and found that the inferred Hubble constant was not uniform. It varied systematically with direction at a level of approximately 9% between the maximum and minimum values. The direction of maximum Hubble constant was broadly consistent with the axis of evil direction, while the direction of minimum Hubble constant was roughly opposite, the antipodal point on the sky. This dipolar variation in the inferred Hubble constant would be expected in a universe with a preferred direction, because the expansion rate in a non-isotropic cosmology would itself be direction dependent. Observers in such a universe, assuming isotropy and applying the standard FLRW framework to compute distances and Hubble constants, would derive different values depending on the direction in which they were looking, exactly the pattern Migkus and colleagues observed. The implications for the Hubble tension are direct. If the universe has a preferred direction and the expansion rate is genuinely anisotropic at the level of several percent between different directions, then the tension between the distance ladder value and the CMB value is not a measurement error. It is a consequence of measuring the expansion in different directions. The distance ladder measurements using Cepheids and supernovae are concentrated primarily in the directions where large numbers of well-characterized host galaxies are available, which is not isotropic on the sky. The CMB-based Hubble constant is a direction-averaged quantity derived from the full sky. If the expansion rate varies with direction, the direction-dependent distance ladder measurement and the all-sky CMB measurement will generically disagree, with the magnitude of the disagreement depending on the amplitude of the anisotropy and the specific sky coverage of the distance ladder sample. A further connection comes from the analysis of supernova peculiar velocities. The Pantheon and Pantheon Plus supernova samples, which compile type Ia supernova observations from multiple surveys and represent the most comprehensive standardizable candle datasets available, have been analyzed for evidence of directional variation in the inferred expansion rate. Several independent groups have found that the residuals from the best fit isotropic cosmology, the differences between the observed supernova brightnesses and the predictions of the standard model, show a dipolar pattern on the sky that is statistically significant at the 2 to 3 sigma level. The direction of the dipole in the supernova residuals is again broadly consistent with the axis of evil direction. This consistency across X-ray cluster distances, supernova distances, CMB temperature maps, galaxy cluster velocities, and quasar spin axes, all pointing in broadly the same direction, and all exhibiting the same qualitative signature of a preferred axis, constitutes the most powerful observational case against the cosmological principle that has ever been assembled. Whether the Hubble tension is fully explained by cosmological anisotropy or whether it requires additional physics beyond a simple preferred direction remains an open question. The magnitude of the anisotropy inferred from the X-ray cluster analysis, approximately 9% variation in the Hubble constant across the sky, is larger than the 8% discrepancy between the distance ladder and CMB values, which in principle could be consistent, but the quantitative relationship between an anisotropic expansion rate and the specific values measured by the SH0 ES and Planck teams depends on details of the anisotropy model that are not yet constrained. What is clear is that the Hubble tension and the axis of evil are not independent problems. They are at minimum consistent with a common underlying cause, and at maximum they are two observational manifestations of the same fundamental departure from the standard cosmological model. Lambda CDM under pressure. The Lambda CDM model, so named for the cosmological constant lambda that represents dark energy and the cold dark matter that constitutes the dominant gravitational scaffolding of large-scale structure, has been the standard framework of cosmology since the late 1990s, when supernova observations first established that the expansion of the universe was accelerating. Its success has been remarkable. The model predicted the precise angular positions of the acoustic oscillation peaks in the CMB power spectrum before they were measured, correctly forecast the baryon acoustic oscillation scale observed in galaxy surveys, and provided a consistent account of the growth of large-scale structure from the smooth initial conditions set by inflation to the complex cosmic web of galaxies, filaments, and voids seen today. For roughly 2 decades, every major observational test of the standard model at intermediate and small scales returned results consistent with its predictions, and the model achieved a status within cosmology comparable to the standard model of particle physics. Not a perfect theory, but a framework so well tested that departures from it required extraordinary evidence. The extraordinary evidence has now been accumulating for nearly 20 years. The axis of evil anomaly was the first serious challenge, identified in 2003 and confirmed by Planck through the 2010 S. The Hubble tension emerged as a statistically significant discrepancy around 2016 and has only strengthened since. A third major tension involves the amplitude of matter clustering, the sigma-8 parameter, which quantifies how strongly matter is clustered on scales of 8 megaparsecs, which is measured to be somewhat lower by weak gravitational lensing surveys and galaxy cluster counts than the CMB-based Lambda CDM prediction. A fourth anomaly is the apparent excess of massive galaxies at high redshift. Objects observed by the James Webb Space Telescope at redshifts above 6, whose stellar masses and star formation rates are in tension with the predictions of standard structure formation models. A fifth is the clustering of ultra-high energy cosmic rays, which appear to show a weak directional preference toward the Centaurus region of the sky, again broadly consistent with the axis direction. None of these anomalies individually constitutes decisive proof that Lambda CDM is wrong. Each can be accommodated by invoking untested systematic errors in the specific measurements, or by appealing to the tails of the statistical distributions generated by the standard model. But the simultaneous presence of multiple independent anomalies pointing in roughly the same conceptual direction, toward a universe that is more structured, more anisotropic, and more complex than Lambda CDM predicts, is a pattern that the scientific community cannot indefinitely dismiss as coincidence. The history of physics suggests that when a well-established model accumulates 3 or more serious quantitative tensions with independent datasets, the most likely resolution is a genuine extension or replacement of the model, rather than the simultaneous discovery of multiple independent systematic errors. The specific failure mode suggested by the axis of evil is the most structurally radical of the Lambda CDM tensions, because it attacks the foundational assumptions of the model rather than its detailed predictions. The Hubble tension, the sigma 8 tension, and the high redshift galaxy excess could in principle all be resolved by modifications to the dark energy equation of state, the neutrino mass sum, or the primordial power spectrum. Changes that preserve the FLRW metric and the cosmological principle while adjusting the contents of the universe. The axis of evil, if physically real, requires abandoning the FLRW metric itself. The FLRW metric is not a solution to Einstein's field equations for a universe with a preferred direction. It is specifically the solution for a perfectly homogeneous and isotropic spacetime. A universe with a preferred direction requires a different class of metric, one that allows the expansion rate and the geometry to vary with direction, and whose predictions for the CMB power spectrum, the large-scale structure, and the distance redshift relation are fundamentally different from those of Lambda CDM. The replacement of the FLRW metric as the basis of cosmology would be the most significant change to the theoretical infrastructure of the field since the adoption of general relativity itself. It would require rederiving the predictions of inflation for the primordial perturbation spectrum in an anisotropic background, revising the theory of Big Bang nucleosynthesis to account for direction-dependent expansion rates during the first few minutes, and reformulating the theory of cosmic microwave background acoustic oscillations in a geometry that does not have spherical symmetry. These are not impossible tasks. Physicists have explored anisotropic cosmological models since the 1960s, and the mathematical framework for doing so exists in the form of the Bianchi classification of spatially homogeneous but anisotropic spacetimes. But transitioning from the FLRW framework, which has been the computational foundation of cosmology for 60 years, to a Bianchi or more general framework would require a comprehensive rebuilding of the quantitative infrastructure of the field, from Boltzmann codes that compute the CMB power spectrum to n-body simulations of large-scale structure formation. Bianchi universes. The mathematical framework for describing a universe that is spatially homogeneous but not isotropic has existed since the 1960s, developed by Luigi Bianchi in the context of the classification of three-dimensional Lie groups. The Bianchi classification organizes spatially homogeneous cosmological models into 9 distinct types, labeled Bianchi-Versust through Bianchi 9, based on the algebraic structure of the symmetry group that leaves the spatial metric invariant. The Friedmann-Lemaitre-Robertson-Walker metric is the special case in which the symmetry group is maximally symmetric, isotropic as well as homogeneous, corresponding to the Bianchi 1 model with equal expansion rates in all 3 spatial directions, or to the more general Bianchi types that happen to have isotropic solutions. Breaking the isotropy while preserving homogeneity leads to the full range of Bianchi models, each of which predicts a different pattern of anisotropy in the cosmic microwave background. The Bianchi 7H model is of particular relevance to the axis of evil discussion. This model describes a universe that expands at different rates in different directions and possesses a specific rotational structure, a global twist of the spatial geometry that causes the CMB temperature pattern to have a characteristic spiral morphology when projected onto the sky. The Bianchi 7H model was brought to prominence in the context of the axis of evil by Jaffe and colleagues in a 2005 paper that searched for the best fit Bianchi 7H template in the WMAP CMB temperature maps. Their analysis found that subtracting the best fit Bianchi 7H template from the full WMAP map substantially reduced the statistical significance of the quadrupole octopole alignment and several other low multipole anomalies simultaneously. The implication was that the CMB pattern, after removing the contribution expected from a mildly anisotropic Bianchi 7H universe, looked more like the isotropic Gaussian random field predicted by standard inflation, suggesting that the anomalies were a consequence of a genuine global anisotropy in the universe's geometry rather than a statistical fluctuation within an isotropic cosmology. The Bianchi 7H model that best fit the WMAP maps required specific values of the anisotropy parameters, in particular a global vorticity of the universe at a level of approximately 1 part in 10 to the 10th in Hubble units. This level of vorticity is not independently constrained by other observations, but it is orders of magnitude larger than what naive inflationary models would predict for the residual anisotropy of a universe that began in the highly symmetric state implied by the near-perfect smoothness of the CMB. The Planck collaboration tested the Bianchi 7H hypothesis in its 2015 and 2018 data releases and found that the best fit Bianchi template required cosmological parameters, in particular the matter density and the dark energy density, that were inconsistent with the best fit Lambda CDM parameters from the CMB acoustic peak analysis. A Bianchi 7H universe with the anisotropy amplitude needed to explain the low multipole anomalies predicted a different angular position for the first acoustic peak than is observed, creating a tension between the explanation of the large-scale anomalies and the precise measurement of the small-scale acoustic physics. This tension is the primary challenge for the Bianchi 7H interpretation. It can be resolved in principle by allowing additional degrees of freedom in the cosmological model, for example, by permitting the dark energy equation of state to deviate from -1, or by allowing a non-zero spatial curvature, but these extensions introduce additional parameters that reduce the predictive power of the model and require further observational tests. The Planck polarization maps provide an important additional constraint because the Bianchi 7H model predicts a specific pattern of polarization rotation across the sky, a spiral pattern matching the temperature template that can be searched for independently of the temperature analysis. The Planck polarization data did not show clear evidence for the expected polarization signature at the sensitivity level available, which the Planck team interpreted as marginal evidence against the Bianchi 7H hypothesis. The interpretation is not definitive, given the systematic limitations of the Planck large-scale polarization data, but it places the Bianchi 7H model in tension with the most sensitive available polarization measurement. Despite this tension, the Bianchi framework remains the mathematically most complete and internally consistent approach to modeling a universe with a preferred direction within general relativity. It makes the connection between the observed CMB anomalies and the global geometry of spacetime explicit and quantitative, and it provides a set of predictions for both temperature and polarization that can be tested systematically as the next generation of CMB experiments improves the sensitivity and systematic control of the large-scale polarization measurement. A light bird detection of the Bianchi 7H polarization spiral at a level consistent with the temperature template, would be definitive evidence for global anisotropy and would immediately constrain the vorticity parameter to the level required by the CMB observations. A null detection at the same sensitivity level would rule out the simplest Bianchi 7H explanation of the axis of evil and push the theoretical burden toward the topology or other frameworks. Cosmic topology. Among the theoretical frameworks proposed to explain the axis of evil without requiring either a violation of fundamental physics or a coincidental statistical fluctuation, the hypothesis of non-trivial cosmic topology occupies a unique position. It does not require any modification of general relativity, any violation of the cosmological principle at the level of local physics, or any preferred direction in the laws of physics themselves. Instead, it proposes that the global shape of the universe, the way space is connected on the largest scales, differs from the infinite, simply connected flat space assumed by the standard Lambda CDM model in a way that would naturally produce the observed large-scale anomalies in the cosmic microwave background. In general relativity, the equations of Einstein govern the local geometry of space-time, how curvature is produced by energy and momentum, and how that curvature affects the paths of particles and light. But the equations of general relativity do not uniquely determine the global topology of the universe, the way space is connected on scales larger than the observable horizon. A universe with flat local geometry, consistent with the Planck measurements of the CMB acoustic peak positions, which require the total energy density to be within approximately 0.5% of the critical density, could have any of infinitely many global topologies. The simplest is the infinite, simply connected flat space, Euclidean 3-space extending without limit in all directions, so that any 2 points are connected by exactly one straight path. But flat 3-dimensional space can also have any of 17 multiply connected topologies, including the 3 torus, in which space wraps around itself in all 3 dimensions, so that traveling far enough in any direction brings you back to your starting point. Other multiply connected flat topologies include the chimney space, which wraps in 2 dimensions but not the third, and the slab space, which wraps in 1 dimension only. The 3 torus is the simplest and most studied of these possibilities. In a cubic 3 torus, whose fundamental domain has side length L, the universe has a finite volume of L cubed but no boundary. Space simply repeats with period L in each of the 3 coordinate directions. Light emitted from a source in such a universe travels outward, and if L is smaller than the radius of the observable universe, approximately 46 billion light-years in the current epoch, eventually returns to the same location from a different direction. The cosmic microwave background in a 3 torus universe would show a specific pattern of correlations between antipodal or otherwise topologically identified points on the sky, the so-called matched circles that have been searched for in the WMAP and Planck data. The matched circles test looks for pairs of circles in the CMB temperature map that have statistically identical temperature patterns, which would be expected if the circles represent the intersections of our last scattering surface with itself in a universe where the light travel distance exceeds the fundamental domain length. Matched circle searches in the WMAP and Planck data have not found evidence for the specific pattern expected from a cubic 3 torus, which places a lower limit on L of approximately 98% of the diameter of the last scattering surface, meaning the fundamental domain must be at least as large as our observable universe if it has the cubic 3 torus topology. This does not rule out a 3 torus, but it requires the topology scale to be so large that the topological effects on the CMB would be subtle, primarily affecting the lowest multipole moments rather than producing the dramatic matched circle signature at intermediate scales. A non-cubic 3 torus, one whose fundamental domain is a rectangular box with unequal side lengths, would produce an anisotropic power spectrum in the CMB, because the finite extent of the universe in different directions would suppress power on scales larger than the corresponding box dimension. If one dimension of the fundamental domain is significantly smaller than the other 2, the quadrupole and lowest multipoles, would be suppressed in the direction of the short dimension and enhanced in the perpendicular plane, creating exactly the kind of planar concentration of power at low multipoles that is observed. The axis of the short dimension of the box would appear as a preferred direction in the CMB temperature maps, the axis of evil. The 2025 analyses by Ulrich and Lustig, building on earlier work by Luminet, Weeks and colleagues on Poincare dodecahedral space models, applied detailed simulations of the CMB sky in non-cubic 3-torus topologies and found that specific aspect ratios of the fundamental domain could reproduce the observed quadrupole-octopole alignment and low quadrupole power simultaneously, without requiring any violation of the local physics of inflation or the standard model of particle physics. The fundamental domain dimensions required were in the range of approximately 12 to 16 gigaparsecs in 2 directions, and approximately 9 to 11 gigaparsecs in the perpendicular direction. Dimensions that would place the topological identification length just beyond the current observable horizon in the short direction, explaining both why the matched circle search failed and why the low multipole anomalies persist. The topology hypothesis has a distinct advantage over other explanations. It makes specific, testable predictions. The most decisive test is through the CMB polarization. In a non-cubic 3-torus universe, the temperature polarization cross-correlation at large angular scales should show the same anisotropic pattern as the temperature maps, with the alignment axis appearing in both. A universe with a preferred direction from topology should also show a specific pattern of hemispherical power asymmetry, more power on one side of the sky than the other, that is consistent with the observed asymmetry in the Planck maps, and the pattern of B-mode polarization at large scales, sensitive to the tensor modes generated by inflation in an anisotropic background, should differ measurably from the standard isotropic prediction. These signatures are within the reach of the Lightbird satellite and the Simons Observatory, and the topology hypothesis is one of the primary science cases driving the design requirements of these next-generation experiments. Finsler geometry and intrinsic anisotropy. The topology hypothesis preserves the local physics of general relativity and modifies only the global connectivity of space. A more radical class of theoretical frameworks, broadly grouped under the heading of Finsler geometry, proposes instead that the anisotropy of the universe is intrinsic to the fabric of space-time at the local level, embedded in the mathematical structure of the metric itself rather than in the global boundary conditions. General relativity is built on Riemannian geometry, in which the distance between two infinitesimally separated points in space-time is given by a quadratic form in the coordinate differentials, the familiar metric tensor of Einstein's field equations. The quadratic form is symmetric and does not distinguish between different directions of travel at a given point. The distance from point A to point B along a particular path is the same as the distance from B to A. This mathematical property, called the reversibility of the metric, is what underlies the physical prediction that the speed of light and the strength of gravity are the same in every direction at every point in space-time, which is the mathematical expression of local isotropy. Finsler geometry relaxes the requirement that the distance measure be quadratic. In a Finsler space, the distance function can depend on both the position and the direction of travel, breaking the directional symmetry of the metric while preserving the other mathematical properties required for a consistent geometry. The generalization is not arbitrary. Riemannian geometry is a special case of Finsler geometry, recovered when the distance function happens to be quadratic. But in the general Finsler case, the speed of light could differ slightly between different directions of propagation, the gravitational potential could have a directional dependence, and the expansion rate of the universe could be anisotropic even in the absence of any particular matter distribution that would create such anisotropy through conventional gravitational physics. The application of Finsler geometry to cosmology was developed systematically by Li, Chang, and colleagues in a series of papers from 2009 to 2015, in which they derived the analog of the Friedmann equations for Finsler cosmological models and computed the predicted CMB power spectrum in the Finslerian framework. Their results showed that a universe described by a Finsler metric with a small anisotropy parameter, typically parameterized by a dimensionless number of order 10 to the -5th or smaller, would produce a quadrupole and octupole alignment consistent with the WMAP observations, while leaving the higher multipole power spectrum essentially unchanged from the standard isotropic prediction. This is exactly the signature observed. The anomalies are concentrated at the very lowest multipoles and are absent or much weaker at multipole numbers above approximately 10. The physical interpretation of Finsler anisotropy in cosmological terms is that the vacuum itself has a preferred direction, a grain in the fabric of space-time that is analogous to the grain of a crystal lattice in condensed matter physics, just as a crystal has different mechanical properties in different directions because the atoms are arranged anisotropically. A Finsler spacetime has different gravitational and electromagnetic properties in different directions because the geometry is anisotropic at the level of the metric. The preferred direction is not imposed by any particular source of matter or energy. It is an intrinsic property of the vacuum state, analogous to the vacuum expectation value of a field in spontaneous symmetry breaking. This interpretation connects Finsler cosmology to a broader class of Lorentz-violating theories that have been intensively studied in the context of quantum gravity phenomenology. The standard model extension developed by Colliday and Kostelecki in the late 1990s provides a systematic framework for parameterizing Lorentz symmetry violations, departures from the perfect directional symmetry of special relativity. In terms of tensor coefficients that multiply additional terms in the equations of motion of the standard model fields. Observational constraints on the standard model extension coefficients from precision measurements of particle physics processes, atomic clock comparisons, gamma-ray propagation from distant sources, and gravitational wave propagation are extremely tight, typically at the level of 1 part in 10 to the 20th or smaller for the electromagnetic sector. If the Finsler anisotropy responsible for the CMB alignment is of the same type as the Lorentz violations constrained by these precision tests, the required Finsler parameter should have been detected or excluded by existing measurements. The resolution of this apparent tension lies in the observation that cosmological Finsler anisotropy, if it exists, would be a property of the large-scale spacetime geometry rather than the local physics of elementary particles. Just as the large-scale curvature of spacetime near a massive object does not affect the local speed of light measured in a freely falling laboratory, a large-scale directional preference in the cosmic geometry might not manifest in the local physics experiments that constrain Lorentz violation. The Finsler parameter relevant to the CMB alignment could be genuinely small in local physics terms, below the detection threshold of current precision measurements, while still producing macroscopic effects on the distribution of temperature fluctuations in the cosmic microwave background through its influence on the propagation of photons across the full Hubble distance of approximately 46 billion light-years. The testability of Finsler cosmology is therefore somewhat limited by this decoupling between cosmic scale and local scale effects. The most direct cosmological tests involve the polarization of the CMB. A Finsler universe would produce a specific pattern of polarization rotation, called cosmic birefringence, in which the polarization angle of CMB photons rotates as they propagate through the anisotropic vacuum. Hints of cosmic birefringence have appeared in analyses of the Planck polarization data, with a rotation angle of approximately 0.35 degrees reported by Minami and Komatsu in 2020 and subsequently confirmed at slightly different values by independent groups. Whether this rotation reflects genuine Finsler-type vacuum anisotropy or is an artifact of the calibration of the Planck polarization detectors remains contested, but it provides a specific observable that the next generation of polarization experiments will measure with sufficient precision to distinguish the two possibilities. The holographic boundary. A third theoretical framework for explaining the axis of evil invokes a concept from the foundations of quantum gravity, the holographic principle, and applies it at the scale of the observable universe. The holographic principle, originally formulated by T. Hooft in 1993 and developed by Susskind and Maldacena into the ADS-CFT correspondence, asserts that the physical degrees of freedom of a region of space are encoded on its boundary surface rather than in its volume, with the information content of a spatial region bounded by the Bekenstein-Hawking entropy formula. 1 bit of information per 4 Planck areas of boundary surface. In the context of quantum gravity, this principle resolves the black hole information paradox and provides the deepest available insight into the relationship between gravity and quantum mechanics. The application of the holographic principle to cosmology is conceptually more speculative than its application in the specific context of anti-de Sitter space, where the ADS-CFT correspondence is mathematically precise. The observable universe does not have an anti-de Sitter geometry. It has a de Sitter-like geometry driven by the positive cosmological constant, and the holographic dual of de Sitter space is not well understood. Nevertheless, several groups have proposed that the cosmic horizon, the spherical surface at the boundary of our observable universe, approximately 46 billion light-years away, plays a role analogous to the holographic boundary of ADS space, with the three-dimensional physics of our universe being a holographic projection of information stored on that two-dimensional surface. In the holographic cosmology framework developed by Afshordi, Coriano, Delarose, Gould and Skenderis, published in 2017, the power spectrum of primordial fluctuations, the spectrum that seeded all subsequent structure formation and whose imprint is visible in the CMB, is derived from the two-point correlation function of a two-dimensional quantum field theory living on the boundary. The theory makes specific predictions for the CMB power spectrum that agree with the Planck measurements at small and intermediate angular scales, high multipoles, but differ from the standard inflationary prediction at the largest scales. In particular, the holographic model predicts a suppression of power at the lowest multipoles relative to the scale invariant spectrum of inflation, which is broadly consistent with the observed low quadrupole amplitude. The axis of evil in this framework acquires a natural interpretation as a consequence of the observer's position relative to the holographic boundary. In a holographic universe, the three-dimensional description of physics is a derived, emergent description. The fundamental description is two-dimensional and lives on the boundary, just as a hologram produces an image that appears three-dimensional but whose properties depend on the viewing angle and on the observer's position relative to the holographic medium. The three-dimensional cosmic microwave background that we observe depends on our position within the holographic projection. An observer at a specific location within the projected three-dimensional space would see a CMB sky whose large-scale patterns were organized around an axis determined by the geometry of their position relative to the boundary, producing an apparent preferred direction, that is, from the perspective of the two-dimensional boundary theory, simply a consequence of the observer's coordinates. The key prediction of this interpretation, that the axis of evil is not a property of the universe itself, but of the observer's position within the holographic projection, is subtly but importantly different from the interpretation in which the universe has a preferred direction as a global property. In the holographic interpretation, an observer at a different location within the same universe would see a different axis, with the axes of different observers related by the geometry of the holographic projection. This prediction is in principle testable through observations of the CMB as seen from a different location, which is not possible directly, but can be approximated by measuring the kinetic Sunyaev-Zeldovich effect in galaxy clusters, which probes the CMB temperature as seen from the location of the cluster gas rather than from Earth. If different galaxy clusters at different cosmic distances see a CMB that has a different large-scale alignment structure, one that changes in a specific way with the cluster's position on the sky, this would be a specific signature of the holographic observer dependence of the axis. The 2025 analysis of the Planck kinetic Sunyaev-Zeldovich measurements by Contreras and colleagues searched for this predicted variation in the effective CMB quadrupole seen by clusters at different positions and found results that were ambiguous at the current sensitivity level, neither confirming nor excluding the holographic prediction. The test is expected to become conclusive with the kinetic Sunyaev-Zeldovich sensitivity of the Simons Observatory, which will detect the peculiar velocity signal from individual clusters with sufficient precision to constrain the direction-dependent variation of the large-scale CMB pattern. Primordial magnetic fields. The preceding theoretical frameworks, cosmic topology, Finsler geometry, holographic cosmology, all address the axis of evil primarily as a geometric or topological phenomenon arising from the global shape of space, the directional structure of the metric, or the observer's position within a projected description. A physically distinct class of explanations invokes instead a dynamical physical field that was present in the very early universe and left a permanent directional imprint on all subsequent structure. The primordial magnetic field. Magnetic fields are observed everywhere in the present universe, in stars, in planetary magnetospheres, in the interstellar medium of galaxies, in the hot gas of galaxy clusters, and potentially in the voids between galaxy filaments. The origin of cosmic magnetic fields is one of the unresolved problems of astrophysics. Small-scale magnetic fields can be amplified by the turbulent dynamo mechanism, the stretching and folding of field lines by turbulent motions in conducting plasma. But the dynamo requires a seed field to amplify, and the origin of the seed is not established. One hypothesis is that the seed fields are generated by astrophysical processes during the formation of the first stars and galaxies. A second hypothesis, and the one relevant here, is that the seed fields are primordial, generated in the very early universe, before Big Bang nucleosynthesis, and surviving to the present as the substrate from which all astrophysical magnetic fields descend. Primordial magnetic field generation mechanisms include inflation, in which quantum fluctuations of the electromagnetic field during the inflationary epoch are amplified by the rapid expansion of the universe in a way analogous to the amplification of scalar perturbations that seeded large-scale structure. The electroweak phase transition, in which coherent magnetic fields are generated by bubble nucleation and collision as the universe cooled through the temperature of approximately 100 giga-electronvolts at an age of approximately 10 picoseconds, and the QCD phase transition, in which a similar bubble nucleation mechanism operates at a temperature of approximately 150 mega-electronvolts and an age of approximately 20 microseconds. Each of these mechanisms produces a magnetic field with a specific coherence length, the scale over which the field is correlated, and a specific spectrum of field amplitudes as a function of spatial scale. A primordial magnetic field with a sufficiently large coherence length, comparable to or larger than the Hubble radius at the time of photon-baryon decoupling, would have a direct effect on the cosmic microwave background. The magnetic field generates an anisotropic stress in the primordial plasma that sources tensor and vector perturbations of the metric, producing gravitational waves and rotational modes in addition to the scalar density perturbations of standard inflation. More directly, a coherent magnetic field of cosmological scale would have a preferred direction, the direction of the field, and would imprint that preferred direction on the distribution of CMB temperature fluctuations through its effect on the acoustic oscillations of the photon-baryon plasma. Specifically, the magnetic field affects the propagation velocity of magnetosonic waves in the plasma differently in directions parallel and perpendicular to the field, breaking the spherical symmetry of the acoustic oscillation pattern and producing an anisotropy in the CMB temperature power spectrum that is concentrated at the angular scales corresponding to the magnetic coherence length. The required field strength for the primordial magnetic field to produce the observed CMB alignment is constrained by multiple independent observations. The Faraday rotation of the polarization of extragalactic radio sources, the rotation of the polarization angle as the radio waves propagate through a magnetized plasma, provides an upper limit on the strength of a coherent intergalactic magnetic field. Planck measurements of the CMB polarization provide constraints on the magnetic field power spectrum through the B-mode polarization that magnetic anisotropic stress generates. Big Bang nucleosynthesis provides a constraint through the effect of the magnetic field energy density on the expansion rate during the first few minutes, which would alter the neutron-to-proton ratio at freeze-out and change the predicted helium abundance. Together, these constraints restrict the primordial magnetic field strength on cosmological scales to below approximately a few nanogauss, billionths of the strength of the Earth's magnetic field, but potentially sufficient to produce measurable anisotropy in the CMB at the lowest multipoles, given the enormous coherence length involved. The specific prediction of the primordial magnetic field hypothesis for the CMB is distinctive. The alignment should appear not just in the temperature maps, but with a specific pattern in the polarization that reflects the geometry of the magnetic field. A coherent field along a single direction produces a specific combination of E-mode and B-mode polarization at large scales, with the ratio depending on the angle between the field direction and the line of sight. This signature is qualitatively different from the predictions of the topology and Finsler hypotheses, and in principle distinguishable from them given sufficiently sensitive polarization measurements. The Lightbird satellite, designed to measure CMB polarization at large angular scales, with sensitivity sufficient to detect inflationary gravitational waves at a tensor-to-scalar ratio of 0.001, would also have the sensitivity to detect or constrain the primordial magnetic field polarization signature at the level required by the axis of evil hypothesis. An additional test of the primordial magnetic field hypothesis comes from its predictions for the rotation measures of high redshift radio sources. A coherent intergalactic magnetic field produces a systematic variation of radio source rotation measures with position on the sky, a large-scale pattern in the Faraday depth of the extragalactic radio sky that can be separated from the local galactic contribution through its smooth, angular dependence. Surveys of rotation measures from the Very Large Array at 1.4 GHz and from the low-frequency array at frequencies below 200 MHz have found evidence for a large-scale coherent structure in the extragalactic Faraday sky, with a preferred orientation broadly consistent with the axis of evil direction. The amplitude of the coherent component is at the level of a few radians per square meter of rotation measure, consistent with a field strength in the range of tenths to a few nanogauss on scales of hundreds of megaparsecs to gigaparsecs. This consistency with both the CMB anomaly direction and the field strength range required to produce it makes the primordial magnetic field one of the more observationally grounded of the theoretical hypotheses. The next instruments. The theoretical frameworks for explaining the axis of evil differ in their detailed predictions for the large-scale CMB polarization, the spatial variation of the kinetic Sunyaev-Zeldovich signal, the rotation measure of extragalactic radio sources, and the gravitational wave background from the early universe. Distinguishing between them and determining definitively whether the axis is a physical reality or an elaborately coincidental artifact requires a new generation of observational instruments with capabilities substantially beyond those of Planck, WMAP, and current radio surveys. Several such instruments are now in various stages of construction and commissioning. The Simons Observatory is the most immediately relevant of the next generation ground-based experiments. located at an altitude of 5,190 meters at the Atacama Desert site in Chile, one of the driest and most radio-transparent locations on Earth. It consists of a large aperture telescope with a 6-meter primary mirror and an array of small aperture telescopes of 0.42-meter aperture. The large aperture telescope is optimized for mapping CMB temperature and polarization at small angular scales relevant to gravitational lensing and the kinetic Sunyaev-Zeldovich effect. The small aperture telescopes are optimized for large-scale polarization mapping, the angular scales most relevant to the axis of evil, using arrays of transition edge sensor bolometers operating at 100 millikelvin, with a total detector count exceeding 60,000 across the array. The Simons Observatory began scientific operations in 2024 and is expected to produce its first major data releases beginning in 2026, with full sensitivity reached by approximately 2028. The specific capability of the Simons Observatory for the axis of evil question lies in its large-scale polarization sensitivity. By observing a substantial fraction of the sky at multiple frequencies from 27 to 270 GHz, with instrumental noise levels roughly an order of magnitude below Planck, it will produce E-mode polarization maps at the angular scales of the quadrupole and octupole with signal-to-noise ratios, sufficient to measure the alignment of the polarization axis with a precision of a few degrees. If the polarization maps show an alignment consistent with the temperature axis at a statistical significance of 3 sigma or above, the case for the physical reality of the axis will be essentially complete. If they show no alignment, the most likely conclusion will be that the temperature anomaly is driven by an unidentified systematic effect that does not couple to the polarization channels. The Simons Observatory's kinetic Sunyaev-Zeldovich program will produce velocity maps of galaxy clusters at cosmological distances, with a sensitivity approximately 10 times better than Planck. This sensitivity will make it possible to test the dark flow signal directly, measuring the peculiar velocity of individual clusters at redshifts between 0 and 1, with sufficient precision to determine whether the Kashlinski coherent flow is real or an artifact of the earlier lower sensitivity measurements. A confirmed detection of the dark flow at the Simons Observatory sensitivity level would constitute independent confirmation of a preferred direction using a qualitatively different tracer than the CMB temperature maps. CMBS-4, the next-generation ground-based experiment planned as a Department of Energy and National Science Foundation-funded facility, extends the Simons Observatory concept with an even larger detector array, approximately 500,000 transition edge sensor detectors distributed across telescopes at both the Atacama site and at the South Pole, providing complementary sky coverage. CMBS-4 is designed to reach a sensitivity level of approximately 1 microkelvin per square degree in temperature and polarization, which would allow the detection of an inflationary gravitational wave background at the level of a tensor-to-scalar ratio of 0.003, well below the current upper limit of approximately 0.036 from the BICEP-Keck array. The large-scale polarization capability of CMBS-4 would provide the most sensitive test available of the axis of evil in the polarization channel, with measurement uncertainties at the large scales dominated by cosmic variance, the fundamental limit set by having only one observable universe, rather than by instrumental noise. The Lightbird satellite, developed by the Japan Aerospace Exploration Agency in collaboration with European and North American partners, and scheduled for launch in the early 2030s, is specifically designed for the measurement of large-scale CMB polarization from space. Its vantage point above the Earth's atmosphere eliminates a source of systematic contamination that affects ground-based experiments, the emission and absorption of microwaves by water vapor and oxygen in the troposphere and stratosphere, and allows full sky coverage without the gaps imposed by ground-based observing horizons. Lightbird will carry 15 frequency bands from 34 to 448 GHz, providing even richer frequency coverage than Planck for separating galactic foreground emission from the cosmological polarization signal. Its primary science goal is the measurement of the B-mode polarization from inflationary gravitational waves, but its large-scale E-mode polarization maps will provide the definitive space-based test of the quadrupole-octopole alignment in the polarization channel. The square-kilometre array, currently under construction in South Africa and Australia, and expected to reach full scientific capability in the late 2020s and early 2030s, will provide the most powerful radio continuum survey ever conducted. Its combination of extreme sensitivity and resolution will detect millions of radio galaxies across the full observable sky, providing the largest sample of jet position angles yet assembled for the study of quasar spin alignments. The statistical power of a square-kilometre array radio galaxy catalogue for testing large-scale spin alignments exceeds that of all previous surveys, combined by more than 2 orders of magnitude. If the alignment signal found in the Taylor, Jagannathan and Meerkat analyses reflects a real coherent structure in the angular momentum field of the universe, the square-kilometre array will detect it at many sigma significance and map its angular dependence across the full sky with sufficient precision to constrain its physical origin. If the alignment is a statistical fluctuation or an artifact of the smaller samples in earlier surveys, the square-kilometre array null result will be equally definitive. The Euclid satellite, launched by the European Space Agency in July 2023 and currently conducting its wide survey of the extragalactic sky, will measure the shapes and redshifts of approximately 1.5 billion galaxies across roughly 15,000 square degrees of sky. Its weak gravitational lensing measurements will map the distribution of matter across cosmological distances with unprecedented precision, and its galaxy clustering measurements will trace the baryon acoustic oscillation scale across a wide range of redshifts. For the axis of evil, the most relevant Euclid product is its measurement of the isotropy of the expansion rate through the angular dependence of the baryon acoustic oscillation peak position. If the expansion rate is genuinely anisotropic, as suggested by the X-ray cluster analysis of Migkus and colleagues, the baryon acoustic oscillation scale measured by Euclid in different directions on the sky should be slightly different, with the magnitude and direction of the variation providing the most precise measurement yet of the expansion rate anisotropy. Euclid's first major data releases, expected from 2025 onward, will provide the most powerful existing constraints on this specific signature of the axis of evil in the late universe matter distribution. The direction of everything. The axis of evil is, at its core, a question about the architecture of the universe on its largest accessible scales, about whether the cosmos is the isotropic, homogeneous expanse that 4 centuries of scientific progress have assumed, or whether it possesses a structure, a grain, an orientation that the standard model cannot account for. After more than 2 decades of observational scrutiny, the answer remains suspended between 2 uncomfortable possibilities, each of which carries profound consequences. The case that the axis is a measurement artifact has been progressively weakened by the accumulation of evidence. The WMAP anomaly survived the transition to Planck with higher sensitivity and better foreground control. The CMB temperature alignment survived the transition from 5 to 9 frequency bands and from 4 to 6 independent component separation methods, each using different mathematical approaches to the foreground subtraction problem. The quantitative challenge to the foreground explanation, that residual galactic emission aligned with the galactic plane could not easily produce an alignment with the ecliptic, which is tilted by approximately 60 degrees from the galactic plane, has never been satisfactorily answered by the artifact proponents. The kinetic Sunyaev-Zeldovich dark flow signal, if confirmed at the sensitivity of the Simons Observatory, would provide an independent measurement of the same directional preference using galaxy clusters as test particles in the cosmic velocity field, a measurement whose systematic errors share nothing with those of the CMB temperature maps. The quasar spin alignment data, accumulated across multiple radio surveys, are now confirmed in several independent catalogues totaling tens of thousands of sources, point in broadly the same direction using the angular momentum of accreting black holes across billions of light-years. The combined probability of all these independent signals pointing in the same direction by chance is, under any reasonable set of assumptions, extremely small. The case that the axis is a physical reality opens questions that are more consequential and more difficult to answer. If the universe has a preferred direction, the cosmological principle is violated at the largest scales, and the FLRW metric, the mathematical foundation of Lambda CDM, is at best an approximation valid only at scales smaller than the coherence length of the anisotropy. The range of theoretical frameworks proposed to explain the physical origin of the axis spans the topological structure of the universe on scales larger than the current observable horizon, the geometric foundations of general relativity, the informational architecture of space-time at the quantum gravity level, and the electromagnetic history of the universe in its first microseconds. These frameworks make different predictions for the next generation of CMB polarization experiments, for the kinetic Sunyaev-Zeldovich signal from individual clusters, for the rotation measures of distant radio sources, and for the directional variation of the baryon acoustic oscillation scale. Within the next decade, measurements from the Simons Observatory, CMB-S4, Lightbird, the Square Kilometre Array, and Euclid will collectively distinguish between these frameworks with a precision that will either confirm the physical reality of the axis or reduce its statistical significance to the point of dismissal. What will not survive in either outcome is the current situation of productive ambiguity. The next generation experiments are not marginal improvements over their predecessors. They represent order of magnitude advances in sensitivity, systematic control, and sky coverage that will either expose the axis as an artifact of limited measurement precision or establish it as a genuine property of the universe at a level of statistical confidence that makes dismissal impossible. Cosmology is approaching a resolution to one of its most persistent and consequential anomalies, and the direction of that resolution will determine whether the standard model requires modest adjustments at its edges or fundamental reconstruction at its core. The scientific community's response to the accumulating evidence has itself been instructive. The initial reaction to the 2003 WMAP anomaly was skepticism bordering on dismissal, an understandable and appropriate scientific response to a result that, if taken at face value, challenged one of the most foundational assumptions of the field. A decade later, after Planck confirmed the anomaly with better data, the community's posture shifted toward reluctant acknowledgement, combined with intense scrutiny of every possible systematic explanation. By the mid-2020s, with the dark flow, quasar spin alignments, hemispheric power asymmetry, cold spot and Hubble tension, all pointing in broadly the same direction, a third phase has begun, one in which serious theorists are constructing detailed quantitative models for a genuinely anisotropic universe, and in which the axis of evil is no longer treated as an embarrassing footnote to the standard model, but as a primary science target of the next generation of experiments. This trajectory, from dismissal to acknowledgement to active theoretical investment, is the characteristic pattern of a genuine scientific anomaly in the process of forcing a paradigm shift. The deeper implication of the axis of evil, the one that gives it its philosophical as well as scientific weight, is what it says about the status of the Copernican principle as a scientific claim rather than a scientific assumption. The principle has never been an empirical result derived from observation. It has been a prior, justified initially by the absence of evidence for any preferred location or direction, and later embedded so deeply in the mathematical infrastructure of cosmology that questioning it felt equivalent to questioning the validity of the scientific method itself. The assumption has been enormously productive. Without it, the FLRW metric could not have been written down. The predictions of Big Bang nucleosynthesis could not have been computed. The acoustic oscillations in the CMB could not have been related to the baryon acoustic oscillation scale in the galaxy distribution, and the coherent quantitative framework of modern cosmology could not have been assembled. The Copernican principle, even if it is ultimately an approximation rather than an exact truth, has been one of the most scientifically fruitful assumptions in the history of physical science. But the purpose of science is not to preserve its productive assumptions. It is to test them against observation, and when observation requires it, to revise them in whatever direction the evidence compels. The history of the Copernican principle itself illustrates this. What began as a revision of geocentric astronomy became, over 4 centuries, a sequence of progressively more radical relocations of humanity's conceptual position. Each relocation was resisted, each was eventually accepted, and each opened a larger territory of scientific inquiry than the framework it replaced. If the axis of evil is real, the next relocation is not a movement away from a privileged position, but something more structurally novel. The recognition that the universe has an orientation, and that our position within that oriented universe, while not central in any geometric sense, is somehow entangled with the geometry of the whole in a way that the past 4 centuries of astronomy did not anticipate and cannot yet explain. The precise nature of that entanglement depends on which theoretical framework, if any, turns out to describe the physical origin of the axis. In the topology framework, the entanglement is geometric. We happen to live in a universe whose fundamental domain is anisotropic at the scale of the full observable cosmos, and the preferred direction we observe reflects the shape of the container we inhabit. In the Finsler framework, the entanglement is more fundamental. It reflects a directionality in the vacuum structure of spacetime that would be present at every point in the universe and would affect the physics of every process, from particle interactions to gravitational wave propagation. In the holographic framework, the entanglement is informational. Our position within the holographic projection determines the apparent direction of the axis, which would look different to an observer at a different location. In the primordial magnetic field framework, the entanglement is dynamical. A relic field from the universe's first microseconds has been shaping the formation of structure ever since, and we are observing its fingerprint in the largest structures that have formed within its influence. Each of these frameworks, if confirmed, would constitute a genuine revolution in the description of the universe. None of them is comfortably accommodated within the standard cosmological model as currently formulated. All of them have specific, testable predictions that are accessible to the instruments being deployed or planned in the next decade. The axis of evil is therefore not merely an anomaly, it is a discriminator, a feature of the universe that is sensitive enough to the fundamental properties of space, time, and topology that measuring it precisely enough can distinguish between theoretical frameworks that differ at the most basic level of their physical assumptions. This is the rare kind of observational problem in cosmology, where the answer, when it comes, will genuinely settle deep questions rather than merely refine the parameters of an established framework. The universe set this pattern in the oldest light it has ever emitted, at a temperature of 2.725 Kelvin, in fluctuations of 1 part in 100,000 that have been traveling for 13.8 billion years to reach our satellites in low Earth orbit. It has repeated the same directional signal in the motion of galaxy clusters at redshifts between 0 and 1, in the spin axes of quasars at redshifts between 0 and 2, in the rotation measures of radio galaxies across billions of light years, in the asymmetric clustering power between the northern and southern hemispheres, and in the variation of the expansion rate measured by X-ray telescopes pointed in different directions across the sky. Whether that signal is a systematic whisper from our instruments or a genuine inscription in the geometry of space itself, the next decade will provide the answer with a finality that the previous 2 decades could not achieve. The axis of evil is either the most elaborate and consistent coincidence in the history of astronomical observation, requiring simultaneous systematic errors in instruments of 5 different types across 3 generations of technology, or It is the first clear signature that the universe we inhabit is not the smooth, direction-free expanse that science has assumed since Copernicus. There is no comfortable middle ground. The experiments are running. The data are accumulating. The answer is coming, written in the polarization of the oldest light in existence, in the velocities of the most massive objects in the universe, and in the orientation of black holes spinning at the centers of galaxies that formed when the cosmos was less than half its current age. Whatever that answer turns out to be, cosmology will not look the same on the other side of it.